This meeting is being recorded.
All right, so we'll get started on the session today. For those of you that have just joined us, I've put a poll up onto the screen. Thank everyone for joining us for our webinar. I'll do the introductions in a moment. For those of you that have just joined us, please feel free to fill out the poll. Give us an understanding of your awareness of the topic that we're going to be discussing today. I'll be ending the poll right after I do the introduction of Chris. Just some housekeeping information. This session is being recorded and will be available after the session along with a survey. Please feel free to watch the video, pass it on to your colleagues, and please fill out the survey so that we have an idea of how to improve our sessions going forward. Feel free to add in questions or chats into the Q&A or the chat section. Most of the questions we'll try to get to at the end of the session, but if there's anything that is urgent, we certainly will try to take those during the session. And with that said, I'd like to introduce our guest speaker today. And I want to thank everyone for attending Fuel Switching with Air to Water Heat Pumps. Chris DesRoches is Applied Product Manager, the HVAC division with an HRI member manufacturer, Mitsubishi Electric. Mitsubishi is an expert on all things heat pumps. Dual fuel systems can provide a building with resilience, redundancy, and flexibility to have the best of both worlds as the industry strategizes to meet the requirements of a low carbon future. So Chris, could you take a moment and, well, you're already on the screen and you've opened your mic, and we can get started. I'm going to end the poll here and I'm going to share the results. And let me know, can you see the results?
Yep, no,
Yeah.
That's interesting. Yeah, it's one thing that's interesting is just the low proportion of people that have actually installed or recommended the technology before. A lot of people know of it, but don't know too many details. And it seems to be one of those things where it just seems very challenging to implement. And we tend to gravitate towards the easy solutions, but in a net zero future, that's no longer going to be the case. And I hope through the webinar today, we'll kind of expand on some of those topics and help everyone understand why dual fuel systems are good.
Okay, so I'm going to stop sharing and I'm going to give you the mic, and I'll handle the questions in the Q&A.
Perfect. Thanks, Loretta. So again, welcome everyone. Thanks for taking the time to join us today on St. Patrick's Day to learn about air to water heat pumps and fuel switching. Just to introduce myself again, I'm Chris DesRoches, Applied Product Manager with Mitsubishi Electric. As Applied Product Manager, I focus exclusively on our hydronics offerings. Mitsubishi Electric has lots of great and innovative technologies like variable refrigerant flow systems. But whenever it comes to solving the HVAC challenge, hydronics is another way that we like to design buildings. And air to water heat pumps specifically are still a little bit of a niche technology, but they're quickly gaining a lot of interest. So with the presentation today, we'll just talk about air to water heat pumps, and we'll kind of go through some, excuse me, trying to get set up here. So we'll just go through the quick recap on the technology and what the design constraints are, and maybe some reasons for not adopting the technology. But really the presentation today is how this technology fits into a low carbon future, including dual fuel systems. So we'll talk about some different examples as we go through it with 2-pipe and 4-pipe and cascade type systems. So just in terms of learning objectives for today, I just hope that, there's kind of 3 key points I'd like to get across. The first one is understanding the concept of fuel switching and the importance of that for high efficiency retrofits of existing buildings. We can go all electric with our designs for HVAC systems, but, and even for net zero buildings, we know how to build them today. It just needs to fit a lot of criteria that we use to evaluate projects like costs and materials and other things like that. But dual fuel systems can be a happy medium between the two. And we'll have some examples as we go through. So I hope to also talk about some design strategies and how to maybe view the air to water heat pump and work around the limitations. And I want to highlight some of the energy and cost savings, as well as emission reductions that are achievable, and how to make the cost evaluation or how to evaluate the carbon savings against carbon tax to make the business case to your clients and customers who are perhaps looking at this technology. So a quick recap on the operating principle for air to water heat pumps. We have, everyone's probably familiar with an air-cooled chiller. So this is a device that will move heat from one location to another using a vapor compression refrigeration cycle. So essentially to provide chilled water to the building, you're essentially rejecting heat through an integrated condenser coil on the machine. In the simplest terms, an air to water heat pump is that machine, but operating with a reverse cycle. So inside the machine, there's a 4-way reversing valve that redirects the flow of refrigerant so that that heat exchanger that was previously providing chilled water is actually providing hot water. And to do this, instead of rejecting heat from the machine, we're actually extracting heat by using it as an evaporator. And essentially to do this, we send refrigerant to the coil of the machine that's at a colder temperature than the atmosphere so that we can actually have heat transfer from one location to another. So on a refrigeration diagram, this is how it would look like with your evaporator extracting heat, the compressor putting work into it, and then dumping that into a condenser. So the metric that we use to describe any heat pump is the coefficient of performance, or COP, which is the heat output of the machine divided by the power input. So if we look at an air to water heat pump that is a reversible chiller, we can essentially, if we think of traditional systems in 2-pipe changeover systems, we would have a typical air-cooled chiller that we use in the summer, and then in the fall, once it gets colder, we turn that machine off and we run a boiler that we run for the winter. And then next spring, we turn the chiller on again. But if a machine exists that can provide both heating and cooling, then this is where we can use the air-to-water heat pump. So we can use that as a chiller in the summer, and in the winter and in the shoulder season, when the outdoor ambient temperature allows for it, depending on how we've designed the system, we can use it to provide heating. And then of course, we still have a backup boiler to run whenever the heat pump can't run. So like a 2-pipe changeover system, we're supplying always hot water or always chilled water in the building. So it's either hot water or chilled water is available year round. So the main design considerations about the air to water heat pump is that unlike a boiler, it's influenced by the ambient temperature. So to get the best value out of applying an air to water heat pump on a project, we need to understand the influence of outside air temperature and how that affects the heat pump operation. And if we understand the heat pump capabilities, rather than trying to fit that into existing designs, we need to design our systems now around the heat pumps if we want to achieve carbon reduction. So there's kind of 3 key points that will vary according to outside air temperature with the heat pump. And that's basically that the supply temperature that the machine can generate will change according to outside air temperature. And this is what we refer to as the operating envelope. We have a capacity reduction from the machine. So as it gets colder outside, it's harder and harder to extract heat from the ambient air. So our capacity that's being generated from the machine is going to reduce. And at the same time, our efficiency is going to reduce because the machine needs to work a little bit harder to extract that heat. So we'll talk about it quickly, but I don't want to go in too much detail for the technical operations. Mitsubishi Electric offers lots of webinars on the topic. So, and also at the end of the presentation, I'll have my information available. So we can always talk about the technical aspects anytime. So for conventional technologies that are available in the market, this is typically what you will find. So while a heat pump from a manufacturer will rate that piece of equipment with perhaps 55 degrees Celsius supply temperature, whenever you look at the operating envelope, you'll see that it's really only able to generate those temperatures between about 3 and 10 degrees Celsius outside air. Once it gets colder from that, it decreases, but typically these machines can usually operate down to -15, and some of them in the market are -20. This is the heat pump that Mitsubishi has, but everything's kind of genericized here. There is a different class of heat pumps as well that can maybe operate with a bit higher temperatures down to lower ambience using innovative compressor technologies as well. So take a look to see what's available in the marketplace whenever you are looking to fit that into your designs. But I hope to kind of demonstrate through the presentation today that it doesn't really matter too much if we're going to apply a dual fuel system. So typically, I usually recommend when making selections to rate the units down to about -10, because at -10, typical machines can provide about 45 degrees Celsius leaving water temperature. And this is basically a balance between having a hot enough temperature to be able to have good heat transfer in convection units in the building in our individual zones versus having a wide operating limits where we can actually use the machine. If we design the heat pump system with 55 degrees, we'd only be able to really use that design temperature between 3 and 10 degrees. And as designers, we want to know that we have the same fixed temperature available at all times. And that's why it's been so easy to design with boilers historically, because they're not influenced by outside air temperature. You know that your condensing gas boiler is always going to provide 140 degrees as an example. So when it comes to evaluating a heat pump technology against our design temperature, so in this example is Toronto, where our design temperature is around -23. Usually, because the heat pump's not able to operate down to -23, people look elsewhere towards different solutions to implement in the buildings. But again, if you already have that chiller boiler system and you have a chiller that needs replacement, air to water heat pumps are very good candidates for retrofit projects where you would size it for cooling, and then whatever you get out of it in heating, you get, and then you have the auxiliary boiler to run whenever you don't need. And you can still run a substantial amount of the season with the heat pump and only running a few hours with the auxiliary boiler, which we'll also talk about coming up. The other point that I wanted to highlight in terms of design strategies would be if we're designing an HVAC system, you could design your system for low temperature, maybe using in-floor radiant heating or heating ceiling panel, something like that, where you could design the entire system regardless if you're operating with the heat pump or the boiler. You could operate at that same lower temperature for a low temperature system design. But another way to maybe look at it as well is if we're operating the heat pump down to -10, and then maybe we have our system needing to operate at warmer temperatures on those extreme days where it's -23. And so if you're using dual fuel systems, there's no reason that you can't use a different supply temperature when the heat pump shuts off. And even in boiler systems, this is typically how we'll run condensing gas boiler systems on outdoor reset, where we're only really running off the hottest temperature that the boiler can produce at the extreme cold conditions. And as it warms up, we have less heat losses from our building, so we don't need to run that boiler as hard. So we can apply the same principle to the air to water heat pump as well. So one extra step that we could do in the design process is essentially look at the performance of our air handlers or fan coil units in the building using a lower temperature, only down to -10, verify that we have enough capacity to meet the heat load at that point. And then whenever we go below that ambient temperature outside, we can just increase the supply temperature from the boiler. The second design constraint that we have is we have a reducing capacity according to outside air temperature. And the one thing I wanted to highlight is the difference between AHRI conditions that these pieces of equipment are typically rated to versus application conditions. So when a manufacturer provides you a standard rating for a product and you don't provide any input to the manufacturer with the temperatures or anything that you want to use, most typically they'll just provide you ratings at AHRI 550 conditions, which will have ambient temperature rating of 8.3 degrees Celsius. So shown here on the graph is the building heating load on the y-axis, and on the x-axis is outside air temperature. So you could size the heat pumps to operate down to -15, and we know that as it gets warmer outside, our building heating load will decrease. And if you look at the AHRI 550 standard rating condition at 8.3 degrees, this is on maybe a milder day, like a little bit cooler than what we're seeing today in Toronto. Actually, it's quite warm. But at AHRI conditions, this is where we have a lot of capacity. But if you look at the heating load, this is kind of at the low end of what our actual building heating load is. So what we can actually do to reduce the sizing of the machine in terms of heating is we can look at a different application rating condition, and we can consider a bivalence point. So a bivalence point just basically means a secondary energy source is being used. So in this example, it would be an auxiliary gas boiler. So we can reduce the sizing of the machine because maybe we only want to run the heat pump down to -7 or -8 degrees Celsius. And that's really a function of the heat pump capacity and the design parameters in terms of the supply temperature that you're going to use. So bivalence point just means the point at which you're going to change over to an auxiliary heat source as well. But by implementing that, we can reduce our footprint, cost, and increase our COP as well sometimes. So the last point that I wanted to talk is just looking at what the COP is comparatively. So this also kind of shows you the operating envelope. So for example, 55 degrees Celsius. The machine has to work a lot harder to achieve 55 degrees Celsius leaving water temperature. And this also shows us that we have a COP, or sorry, we only have this operating between about 3 degrees and 10 degrees Celsius outside air temperature. So basically, the lower the supply temperature that the machine's working at, it doesn't need to work as hard, so the efficiency goes up. So if we look at a point of about 0 degrees Celsius, which is average winter day in Toronto, if we're designing with a 45 degrees Celsius leaving water temperature, we'll have a COP of 2.8, which basically means we put 1 unit of electricity into the unit, we get 2.8 units of heat out. But if we're designing with a 40 degrees Celsius, so maybe instead of using convective fan coils, we're using in-floor radiant heat, we can actually increase our COP by 10%. And the important thing to remember about the COP is that if you have an increase in 10%, that also means if you're comparing it to an electric boiler, it's 10% less cost because you're getting more bang for your buck in terms of the energy that you're using. And then if we want to even go down to 35, not only are we extending the operating limits where we can use the machine, but we're still increasing the performance again by another 10%. So just from going from 45 to 35 to switching to a radiant inflow system as an example, we can increase our efficiency by about 20%. So superimposed on the background here is actually the weather data for Toronto. And I have a couple slides coming up with just various cities within Canada. But in Toronto, yes, our design temperature is -23. But we see we have relatively few hours where it's below -15 or even -10 for that matter, where the heat pump can't run. So again, in most cases, you're probably only going to size the heat pump anyway down to, anywhere from -5 to -10 degrees Celsius, again, depending on the project. So this is similar weather data, but for Vancouver. So Vancouver is quite a different market. They have a more milder climate, so they're more of a mature heat pump market. And there's lots of great things happening in Vancouver. And I truly believe that they're setting the stage for what net zero is going to mean for the rest of Canada into the future. But that's because they have a bit of a better climate where they can actually do that. So Vancouver, lower mainland, typically you can only get as cold as -8 degrees or so. So in most cases, they're actually eliminating natural gas boilers and backup boilers and designing a lot of new buildings actually with these types of heat pumps. If we look at Toronto, same example that we had before, yes, our design temperature is -23, but this is the last 3 years on average, which doesn't include this winter that just passed. These go with our fiscal year that ends in April. So we'll be updating it soon. And it was a little bit of a colder winter this year in Toronto. But still, if you look at the times really between -10 and +10, going back to the first example where I said, at -10, you would have a 45 degrees Celsius supply. Even if you just look between -10 and +10, that's over 4,600 hours throughout the year. So 50% of the year where we're in heating season, that we can get good COPs and good supply temperatures from the heat pump. And for the few hours where it's colder than that, we run off the auxiliary boiler. But rather than have to run the machine at colder temperatures with a lower COP, if we already have that gas boiler sitting in there, we can just switch over to that. And we're balancing our costs and our energy management throughout the year. Montreal is a little bit more of an extreme climate. So if we look here at times where it's below -10, we're talking maybe about 600 hours, but still between that -10 to +10 range, we're at about 50% of the year. So if we look overall through Vancouver, Halifax, Toronto, and then maybe into some more extreme climates like Montreal and Calgary, we look at the amount of time like Calgary is about 950 hours or so where it's colder than -10. But on average, on all these cities, more than 50% of the year, we're spending between -10 and +10, where it's good heat pump temperatures. So with all the weather data, really the main point that I have is people get very hung up about cutout temperatures on heat pumps. And if you want to keep designing hydronic systems, that means that we need to remove natural gas from the systems. There's other technologies that we can look at with heat pump compressor technologies in our ventilation or our air handler equipments, rooftop units. VRF systems are good solutions. But again, air to water heat pumps, really just think about it as another tool in the toolbox whenever you're trying to design systems with hydronics. But electrification and reducing carbon are quickly becoming hot topics these days. And the solution to that is not as simple as just changing out every single gas boiler that's in the existing building stock and changing those to electric boilers. Our infrastructure and our electrical grid can't support that, not to mention the changes that are also going to be coming in terms of electric cars that need to go into it. That's a whole topic altogether, but just to talk about how to compare efficiency of natural gas, electric boilers, or electric heat pump. If we look at a natural gas boiler, we have condensing gas boilers that are kind of the norm. Starting 2025, you'll only be able to get condensing gas boilers. And these will typically have efficiencies of 95 to 98%. And it's really based off the return temperature and the load of the system. But your COP or coefficient of performance for this is going to be less than 1. So it will be 0.95 for a 95% efficient boiler. And if we compare an electric boiler to that, for an electric boiler, the COP is always 1. So you put 1 unit of electricity into the machine, you get 1 unit of heat out. So a thermal kilowatt hour provided from an electric boiler or a natural gas boiler or an air to water heat pump, that's basically the same thermal kilowatt hour that's being provided. But when you look at the heat pump, you have a COP anywhere from 2 to 4, depending on the outside air temperature, since it's also using electricity. So If the objective is net zero, we need to get natural gas out of the buildings. We can't just change all the natural gas boilers to electric boilers. And because the air to water heat pump will always be more efficient than the electric boiler by a factor equal to the COP, which can be anywhere from 2 to 4, then we know in some shape or form heat pumps will be part of the solution. There's improvements in the technology where manufacturers are continuing to push the limit to get them operating down to colder temperatures with higher COPs, and it'll continue to improve over time. But in this intermediary decade, dual fuel systems do make a lot of sense, especially if you're talking about a building that already has a gas boiler and it's being upgraded to, rather than replacing a chiller like for like, upgrade it to a heat pump and use it within the limitations. And when it's too cold, then you just run off your natural gas boiler. So if we want to do a carbon analysis of what this will look like across Canada, different markets produce electricity from different means. So in green here is showing the emission intensity if you convert the electricity efficiency generation using kilowatt hours, and then red is showing the same for natural gas. Usually natural gas is in gigajoules or cubic meters, so this is showing it converted to kilowatt hours to show the same amount of energy that's being provided to the building. So you're comparing apples to apples. So as you'd expect in places like BC, Ontario, Quebec, natural gas has way more emissions per thermal kilowatt hour than electricity. If you look at places like Alberta, Nova Scotia, and Saskatchewan, what this is actually telling us is that electricity has more emissions than what a electric boiler. So again, this is using a COP of 1. So only looking at an electric boiler. This isn't taking into account the COP from using any kind of heat pump technology. But in Alberta, you'll see it's almost 3 times more emissions to use electricity than natural gas. So if you have a COP of 3, then it's about the same. So what's going to happen in these places is they're going to continue to improve the electricity supply so it has less carbon emissions by converting, Alberta uses a lot of coal, so they'll convert some of those plants to natural gas. They'll add solar and wind to the mix as well. So it's just interesting that it varies according to province, but even despite that, Nova Scotia's interesting market because they have a little bit more of a milder climate, and they're starting to look at air to water heat pumps specifically in a lot more detail because they know that they're going to be improving their efficiencies over time. So if you take into account the heat pump of the COP and you look at these energy emissions for electricity or natural gas, we know for that same thermal kilowatt hour that's being produced, what our carbon emissions are. And whenever you normalize that to what the heat pump emissions are, taking into account the COP, and divide the electric resistive boiler by the heat pump COP, and do the same with natural gas, you can express the different energy sources in terms of how many more emissions are produced for providing the same amount of heat. So our heat pump is normalized, so that's 1 all the time, and on the x-axis here we have outside air temperature. And if we compare that to an electric boiler, it's basically 2 to 4 times more emissions based off the values for Ontario. And I mentioned that before, that the heat pump is going to be more efficient by a factor equal to the COP. And then if we look at natural gas, that's 12 to 23 times more emissions by using natural gas. So even at -10, when it's the COP for the heat pumps at its worst, it's still 12 times less emissions for the same amount of heat provided. And whenever it's warmer and easier to extract heat, you're not going to be providing heating to a building at 20 degrees, but maybe you can use it for domestic hot water, which we have domestic hot water loads year round. We're talking 23 times more emissions. So that's based off Ontario. British Columbia has even cleaner power, about half the emissions of what we have in Ontario. So that goes up to about 25 to 47 times for a natural gas boiler. And if we look at Quebec, who gets most of their energy from hydro, this it's 360 times less, and you actually can't really see the heat pump or the electric boiler compared to natural gas, because in Quebec, it's about 1.2 grams per kilowatt hour produced. So, so it's quite interesting. So again, it just depends on which climate that you're looking at. So I just wanted to summarize quickly how to make the financial evaluation if you're doing that. So if we look at comparing an air to water heat pump to a conventional boiler, that same thermal kilowatt hour that's produced, we want to find out how do we compare natural gas to electrical input and take into account the COP. So if we look at our electric heat pump, we will look at what are dollars per kilowatt hour electricity that we're paying. And if we divide that by the COP, that tells us how many dollars we're paying for 1 thermal kilowatt hour provided from the heat pump. And if we look at natural gas and we convert our pricing into dollars per kilowatt hour of natural gas and divide that by the boiler efficiency in terms of percent, that's how much money we're paying for that one same thermal kilowatt hour provided from the natural gas boiler. So we can rearrange that equation and figure out what's my break-even COP that I need to break even. And what we can actually do is we can express that in terms of the ratio between the price for kilowatt hours for electricity versus natural gas. And you would have this equation here. So natural gas boilers will vary in efficiency anywhere from 80 for an older boiler technology and as much as 95%. So we can actually plot different lines using that equation, and we can find out based off our price ratio what COP we need to break even for those equations to equal each other. So if we look at this equation, dollars per kilowatt hour divided by dollars per kilowatt hour natural gas times the boiler efficiency, and putting in the prices, the conversion factor for cubic meters to natural gas kilowatt hours is 10.1. The only point on price is I'm using here 35 cents per cubic meter and 12 cents per kilowatt hour average on electricity. What I'd recommend is you just take a look at your utility bills, because although the utility might say that your effective rate of natural gas is 10, 15 cents, whenever you take into account all the delivery charges and distribution charges, you'll see that that number is closer to 30 to 35 cents in some cases, and do the same for electricity as well. Electricity is really hard because we have time of use pricing in Ontario. But again, that makes sense for the heat pump, because at nighttime in the winter is typically when we need the most amount of heat, and that's when electricity is the cheapest as well. So it's all relative to it. My intention here is just to provide the metrics of how you make that comparison, but essentially you figure out what your cost ratio is, and then you draw a horizontal line, and then based off if you're comparing that to a 95% efficient boiler, you just look down and figure out, okay, I need a COP of 3.25 in order to break even. Or if you're looking at an 80% boilers, it's a little bit lower, 2.7. But again, the other thing to consider about this would be that's your break even point, but you have more hours. So a COP of 3 from the COP charts that we looked at before might correspond, depending on the temperature, to an ambient temperature of, say, 5 degrees. So below 5 degrees, it's more expensive to run a heat pump. But you also need to consider the average throughout the entire year. So there's a lot of hours between 5 and 10 degrees where you're actually saving money compared to natural gas. And between, say, 5 degrees and 0 degrees or -5 degrees, you're paying more for electricity than natural gas, but the two will kind of balance each other out. So it's no longer about just a simple binary way to look at it of this way or that way. We need to start looking for solutions that involve different mixes of dual fuel systems and energy management strategies as well. So now just on to some applications. So if you're going to size a heat pump for 2-pipe systems and changeover, depending on what your total capacity is, in most cases, you're going to size the heat pumps based off the cooling requirement. So you can use 1, 2, 3, as many units as you need to meet the cooling load, depending on the size of machines that you're looking at. Different manufacturers offer different sizes. But basically in the summer, you run all the machines in cooling. And in the winter, you run all the machines in heating when the temperatures or the design allows for it. And whenever it's too cold to run the heat pumps due to ambient temperature cutout, or perhaps the supply temperature you're designing with is 45 degrees, so below -10, you'd have to run an auxiliary boiler. You already have that boiler in the system and you can change over. So that's pretty simple integration into an existing central plant. So this is an example for a project where there's a chiller that needed to be replaced, and using bin hour analysis, we looked at what the total carbon savings would be. So the whole message with these types of products is, rather than replacing air-cooled chillers like for like, upgrade them to a reversible heat pump. There's a marginal cost associated with that. Size them for cooling, and whatever you get out of them in heating you get, and you have the auxiliary boiler as part of the system anyway. So changing that chiller to 2 heat pumps, you could then look at what the total amount of carbon's offset, which in this case was about 118 tons per year that was offset from carbon. So the other part that I wanted to get at, rather than looking at the utility costs, we have the carbon tax. And on April 1st, that carbon tax is going to go up to $50 per ton. And once the new legislation goes into place, that'll see the price rising to $170 per ton by 2030. But essentially, under the existing scheme that we have of the tax increasing by $10 per ton per year, that translates into approximately 2 cents per cubic meter for increased pricing to natural gas. So once the price structure goes up to $15 per ton, we're looking more at 3 cents added per cubic meter of natural gas year over year. So we see that the price of fuel is going to increase over time. Electricity will also probably rise over time. So to do a fair comparison, you should also forecast that. But if we look at the annual savings based off 118 tons in 2022, that would be roughly $6,000 per year. By 2025, that would be $11,000 per year. And by 2030, that's $20,000 per year. And then shown here on the right is just the cumulative savings. So assuming that you're going to do some sort of retrofit project on a chiller now, by the time 2030 rolls around, when the tax is at its highest, that's still $116,000 of cumulative savings that you've seen. So that can quickly pay for the cost of the chiller within that first decade. Plus now your system and your building is future proofed. So once that machine's at the end of its life, 15, 20 years from now, you're going to replace that with the next generation of equipment that will be available in the next 10 years or so. So it makes a lot of sense to look at this technology for dual fuel systems in the current decade that we're in. So now I just wanted to talk about 4-pipe systems. So should be finishing up in about 10 minutes. Have lots of time for questions. So 4-pipe systems, most modern buildings nowadays are cooling dominant. So this means that we need cooling available for the majority of the year. 4-pipe systems are just essentially 2-pipe systems that don't change over. So you would have a dedicated chilled water system and a dedicated hot water system. So in order to understand how what carbon savings can be implemented, what we wanted to do was adapt reversible heat pumps into this application and see what the savings are. So while we do need heating and cooling year round, whenever it's very cold out, we don't really need as much chilled water in a building that's operating on hydronics. Maybe we need ventilation, but we can do things like free cooling and implement other technologies on the ventilation side to cut the energy down. Really, when we do have the requirement for both heating and cooling is kind of in the summer, because typically what we'll do in air handlers is we'll do reheating strategies. So we will overcool the air and then heat it back up in order to remove the humidity from it. So this is an example for an energy modeling study that we did that does not include domestic hot water. This is just space heating and cooling. But in the summer, you still have a small amount of load that's typically required. Now, this looks a bit simplified because this is hourly data expressed in terms of the average peak heating load based off outside air temperature. But in reality, our heating and our cooling loads are going to fluctuate throughout the day. So whenever machines turn on or off, whenever lots of people go into a room and it's occupied and there's more heat load and you need to remove that heat, this is really occurring dynamically. So we're shifting up and down throughout the year as our loads are changing throughout the day. And then obviously in the summer, we don't have the solar loads at nighttime. So any cooling system doesn't really need to operate as much at the nighttime. And also buildings are probably doing remote setback for office buildings and things like that. So to adapt reversible heat pumps into a 4-pipe system, what we wanted to understand to do an energy modeling study is we looked at a building from ASHRAE 90.1 standard 2004 to find a building that was representative of a chiller that was perhaps coming up to the end of life and needed to be replaced. We actually tried to do this first just off 2-pipe changeover to see how that would look, and we quickly found out that that wasn't possible. We weren't able to meet the cooling loads and the heating loads. So what we came up with was a system that had 3-way valves on the inlet and outlet of each unit. And this essentially allows you to connect all the units in parallel and have them independently work into the heating loop or into the cooling loop. And in this instance, because you already have the auxiliary boilers for the same reasons that we talked about before, the auxiliary boiler just essentially makes up the difference. So in this instance, you would size all the units based off cooling. You operate and stage the machines to meet the cooling requirement for the building. Any units that don't need to be staged into cooling can then be staged into heating and can be used to meet the heating requirement of the building to offset any potential boiler usage. And whenever the heat pumps can't keep up with the heating demand in heating, however many of them are staged, the auxiliary boiler just takes over and makes up the difference. And this actually ended up being quite a neat system. So this chart here, basically the blue line shows the peak cooling demand at the building, so what's required. And the blue bar is showing the cooling capacity available, in this instance in July, August, September, of 3 machines staged into cooling. Now, this isn't meeting the line here because this is using the average peak monthly temperature, and this is showing an instantaneous peak based off the calculated energy model. But you see in January, you have no cooling requirement, so you stage all 3 units into heating and you're meeting your heating requirement. Same in February, and then in March, whenever you start to get a little bit of cooling and heating, you stage 2 machines into heating and 1 in cooling, and you can meet both the loads. In reality though, in March, this peak heating requirement doesn't occur at the same time as this peak cooling requirement. This is maybe a warm day like we're seeing today in Toronto, where it's supposed to be 15, 16 degrees. So we're going to need to stage our system into cooling, and we're not going to have a lot of heating requirement. So the important point about this, and the point I want to get across, is that the building loads are dynamic, and so must be the heat pump system. And traditionally in traditional cooling and heating systems, we solve that problem with variable frequency drives, and we modulate our systems down. But now the time's coming where the objective is to reduce carbon, and we can reduce carbon emissions in a building by reducing the supply temperature through outdoor reset, slowing our flow rates down, but we're still burning natural gas and fossil fuels in that building, which is not compatible with a net zero future. The building requirements are changing over time so that the metric is greenhouse gas emission intensity, and the targets for those for new construction is continuously being lowered and lowered and lowered. We can overcome that so much by building envelope upgrades, applying different technologies together, but ultimately we do need to find ways to reduce carbon. And the dual fuel system, again, is a good medium ground where you have that resiliency to run the boiler for those few hours where it's very cold, and the rest of the time when it makes sense to do so, you run off the heat pump. So again, just showing here the boiler will kind of just fill in any missing instances here with your auxiliary boiler. So what we actually found for this one, so we modeled the same building, just basically the chiller that needed an upgrade or replacement, and we looked at adapting the heat pump system into it. So we took that same building that was designed and we analyzed it in the Vancouver, Toronto, and Montreal climates. So in Vancouver, we were able to model that with operation down to -7 and actually eliminate the auxiliary boiler. In Toronto and Montreal, we just sized the system to operate down to -10, operating with a 45°C supply temperature. And even for the energy use intensity overall, we were able to reduce that by about 23% in Toronto and 20% in Montreal. And overall, we had natural gas reduction of about 50% in Toronto, 42% in Montreal, and 55% in Vancouver. So if we want to look at our electric use intensity, we did have an increase in electricity. So that's because we're adding more kilowatt hours to the heat pump that were previously being met with natural gas. And then in terms of natural gas use intensity, we're also seeing a decrease in that. So basically a greenhouse gas emissions, 50%, 39%, and 39% in Toronto and Montreal. So very similar. And for natural gas usage, about 50% reduction in Toronto and 42% in Montreal, like I mentioned earlier. So on the cost side for this type of system, it's a little bit different with sophisticated energy management controls. But if we just look at the same methodology that we looked at before in terms of total carbon savings and annual savings versus cumulative savings due to a rising carbon tax, based off the total carbon savings for these 3 buildings for Vancouver, Toronto, Montreal, we have about 200 tons annually offset per year. And if we look at a standard air-cooled chiller, the replacement cost to replace just with a like-for-like chiller, that might be somewhere around $1,200 per ton, and the air-to-water heat pump might be around $2,000 per ton. This really varies depending on project size, scope. So take these with a grain of salt, but if we just consider an incremental cost of maybe $800 per ton for a 175-ton system, we're talking somewhere around $140,000. There's obviously going to be some ancillary components in that as well, but just off the same methodology that we looked at before, we're talking about over $200,000 in all 3 climates of savings by 2030 just due to carbon tax alone. So it's what is a good design? That's very subjective, but the metrics of how we're defining good projects nowadays is kind of being turned upside down, and we're starting to really get focused on carbon and reducing carbon. And whenever you think about it, for the federal government to implement a simple carbon tax, dollars per ton, I believe this is the intention of it, so that as designers or engineers or building owners, if you're building a new building and you're going through the design process and looking at, okay, what's option A, what's option B, how much carbon are we saving with option B, how much more money does it cost versus what's the tax? It's a simple way to just do quick napkin numbers to figure out which direction you're going to steer your design towards. So I just have a couple more slides left, just different applications. So 2-pipe applications. One system that's pretty nifty is water loop heat pump systems. So these are common in Toronto, where in individual condo suites, you'll have water to air heat pumps that will basically pull heat or add heat to the loop, depending if they're in summer or cooling. If they're in heating or cooling. And this is a good system because you can basically provide a 2-pipe system throughout the building, but provide 4-pipe comfort. So one unit might be in heating while this one's in cooling, and they're actually exchanging the heat through the water loop between the two. And on the penthouse, you would have a boiler to add heat to the system and a cooling tower to reject heat from the system. So air to water heat pumps are great candidates for these types of systems, where you can replace the boiler with the heat pump and still have the auxiliary boiler for those few times where it's too cold to run the heat pump. But these systems operate at lower temperatures, so typically around 30 degrees Celsius or so. So if we look here, this means that not only do we have a really high efficiency, as it gets warmer outside, our heat pump could be providing a higher temperature, but it doesn't need to, because by maintaining the heat pump operation at the lowest temperature, we're ensuring we're always maximizing our COP. And then similarly on the cooling tower side, we can maybe downsize the cooling tower and use a smaller cooling tower. You would have to compare the heat pump operating in cooling mode, which has compressors and a higher consumption, and compare that to a cooling tower that only really has a fan load. But maybe one avenue is to downsize your cooling tower, have it run more efficiently, and then kind of use mechanical cooling from the heat pump as a second stage of cooling for those very warm days. That's why it's called an applied product, is there's a lot of different ways that you can use it, and it's all subjective to the design of the building and what the objectives are. So aside from that, domestic hot water preheat is a good solution that you can use and tie into it and offload spare capacity in warmer temperatures as well. Whenever you have less building space heating load that you need to maintain, you can operate the heat pump to provide domestic hot water preheat and reduce natural gas for the final tank that needs to be stored at 60 degrees Celsius for Legionella. In terms of medium temperature applications, we're talking about convective fan coil applications, terminal units, air handlers, and this is where we do want to have a bit of a warmer temperature. So in those instances, we can operate down to about -10. VRF is another good solution, and Mitsubishi has air source and water source VRF. Typical VRF technologies that are available can now operate down to -30 or so. So there's entire buildings that are going up with VRF systems, and that's great if you want to do a VRF design. Typically for water cooled, those will be geothermal systems. So another way you can look at using the heat pump is basically for water cooled systems where digging a geothermal well is not feasible. Air to water heat pumps can be a good alternative. It's basically the same thing as the water loop heat pump system, but instead of these water to air units in each suite, these would be VRF water cooled condensers with the VRF systems connected to them that are heating and cooling multiple spaces. So with VRF systems with heat recovery, you have heat recovery between individual units, and then you also have heat recovery through individual condensers through the water loop. So for example, if one floor is operating in cooling and the floor below it's operating in main heating, you're actually exchanging heat between these two, and then really the central plant really just needs to add or reject heat from the overall system to maintain that condenser water loop temperature. Lastly, I just wanted to touch briefly on a different type of cascade system, and for everything to do with heat pumps, we were talking about using medium temperature around 45 degrees to do space heating or cooling. Retrofit systems, if you don't want to change all the individual fan coil units or coils and air handlers for an older system that's operating at say 180 degrees Fahrenheit, which is typical in a lot of buildings. One way that we can get around that is with a cascade system of a different type. So this is actually using an air to water heat pump on the primary loop, operating at the lowest temperature possible to maintain just 35 degrees year round. And then you can actually feed that into a water to water heat pump designed for high temperature lift, where the air to water heat pump is actually supplying water to the evaporator side of this. And through the compressor in this water to water unit, you're actually boosting it up as high as 80 degrees Celsius. So this can be a good solution as well for those high temperature applications, or perhaps process applications where you need a lot of domestic hot water for factories or something like that. So it's just another way to skin the cat. But if the objective is looking at carbon, or reducing carbon, sorry, and keeping our systems hydronics, air to water heat pumps are a tool that we will start to see more and more in the future. Yes, there are challenges with it, but we need to work within those challenges and think about solving problems a little bit differently. So thank you for your time. That's all I had today. Here's my contact information. I'm always happy to talk about heat pumps. With it being a niche technology, I do a lot of different webinars like this, just educating and working on designs or applications for engineers, contractors, developers. So if you have any questions or you want to just chat about heat pumps, feel free to shoot me an email or give me a call. We have a good hydronic heat pump offering. So if you're interested in exploring that, you can find details at climateavenida.ca. And we've just published a new 4-pipe case study as well, the hybrid 4-pipe system I was talking about. We have a case study that's on our website now. I'll post a link in the chat as well. But if you have some time, check it out and drop me a line if you want to connect. And so thanks everyone for your time. Thanks for joining today. And we can open it up for questions.
All right, Chris, thank you so much for that. I've got a couple questions. One is an air to water heat pump is low temp heating applications, correct? Only so only suited for rads and air handler designed for low temperatures. Oh, I think your sound is off. No, we still can't hear you.
Sorry.
Oh, there we go. There we go.
There we go. Sorry. Yeah, I mean, if you want to be black and white about it, yes. The lower temperature, the better, the more easy it's going to be to adapt into the system, the more efficient it's going to run. You can have the heat pumps work with boilers and maybe have the boilers increase the heating as well. That I didn't talk about that today, but there are applications for that as well. But generally, yes. But that's the direction that the hydronics industry is moving towards. And we saw the same thing whenever we used to have old boiler systems at 180 degrees, and then condensing gas boilers came in because they were more efficient. And then we saw our heat emitters getting big, we saw our flow rates increasing. But to have that higher efficiency on the boilers of 95%, industry had to adapt to that, and that's more or less the norm. And starting 2025, all you can get in Canada is natural gas boilers. Air to water heat pumps, in my view, are just the next continuation of that but now reducing carbon is kind of paramount. So it's moving in that direction.
All right. I have two other questions. What about defrosting during winter? How much does that affect the heat pump's ability to provide heat?
Yeah, so I usually get this question, so I prepared another slide. Defrosting is something that does happen. It's a phenomenon with any kind of air source heat pump, because what happens is your evaporator is getting very cold. And if you have humidity, you'll have that humidity actually condensing and forming frost on the coils. Same thing as having a can of Coke on a hot summer day. And within the AHRI standard, this is something I always make sure to mention. Within the AHRI standard, it doesn't actually account for the effects of defrost, so the performance measurements kind of taken after the defrost cycle is kind of finished. With the European standard, though, actually, it's taken during the defrost cycle, so you're kind of accounting for that penalty, because what happens as you get frost and ice forming on the coil, you will inhibit heat transfer, and you'll have less of a COP. So there's just two different performance standards. So the European standard is actually EN 14511. That the way the test standard's done takes that into account. So if you're looking with manufacturers, it's important to also look at the ratings in accordance with the European standard that will account for those changes in or the effects of defrost, so that you're, depending on how you're sizing it, you're taking that into account to know that you're covered on those colder days.
Right. We have another question as well. Can heat pumps work with boilers at the same time to reduce the size?
Yeah, so in one of the first slides that we had about that bivalence temperature, I'll just skim back very quickly here. So this guy here. So this is showing changing over based off auxiliary boiler on the left, or to the right, we're operating off heat pump. But technically the heat pump can operate still for this portion here below the blue line. So really the boiler only needs to, if you want to fill in this part here. But if we're looking at the boiler, it's much simpler in terms of adapting it into the design, that the boiler will just take over completely. You can, however, have the two sources work together, but the only design consideration that needs to be taken into account is that for the auxiliary boiler, it's not influenced by outside air temperature,
Okay.
but the heat
Go.
pump is. So they're going to operate at different temperatures as it gets colder. So if you assume that you have two units operating at 50-50 load, the boiler is still going to deliver 60 degrees, we'll say, but the heat pump might only be delivering 50. So then you have 55 degrees leaving. So that just needs to be taken into account for your design.
Okay. And do you have, I have another question here. Let's go back here. Do you have any study for mid-rise or high-rise buildings that would address the impact of electrification measures such as air source heat pumps on building infrastructure and grid capacity?
That's an interesting question. In terms of low rise, that's why we chose the hotel, because that was a hydronic building that had an existing chiller and boiler to adapt the heat pump into. So a hotel is very similar to multi-unit residential for low rise. If you're talking about high rise, the challenge with air to water heat pumps is usually footprint on the roof. But in terms of, like, that's why I wanted to summarize electric boilers. Heat pumps always make sense over electric boilers if you can deal with the ambient temperature thing. But the thing that I didn't really talk about is the peak kilowatts that are being added by the heat pump. And that will factor into the electricity charges as well with your demand charge. But it would be interesting to see how everything works out. And I think you need a little bit more detailed modeling. So it's not something that we had covered. We tried to simplify the study that we did, but we're always, with different projects that we have going on, we're continuing to research and do some data monitoring to monitor this stuff long term to really understand how it fits in to the grid as well. And the other thing too is energy storage. So buffer tanks, if you can generously size your buffer tanks for a building as part of a retrofit, then this can actually be used to your advantage for energy storage. So maybe those few hours in the middle of the night where it's too cold for the heat pump to run, if you do have individual loads that are turning on or off, you can draw from your buffer tank before having to turn on the boiler. And then when the ambient temperature increases, then you can switch back the heat pump to charge that tank back up to temperature and hopefully reduce electric or natural gas backup from running.
Okay. We have time for one more question. Do you have a case study on condo system, cooling tower and boiler loop as a system at 75 to 100 degrees Fahrenheit? And then he just added condo has heat pumps in the suites.
No, but that would be something I'd be very interested in discussing further. So if you want to reach out to me for that, we can do some analysis and design selections on paper. So feel free to reach out and send me the information. And all the examples from the webinar, and I have other examples, are usually just from cases of people reaching out to try to understand what the solutions are. And sometimes based off the design objectives, they don't meet the requirements, and other times they go ahead as projects. So in terms of high rise, the one example I have with 120 tons, that's something that we're supplying, and we'll have a case study released on that after it's been commissioned and everything, probably a year or so from now. But other applications, I'm very interested in water loop heat pump systems and seeing how those fits in, because in my opinion, those are one of the better applications for air to water heat pumps. So if you have a project, feel free to reach out and I'd be happy to chat about it in more detail.
All right, then. I think that's all the questions. Chris, do you want to put up your last slide just so people can maybe take a screenshot of how to get a hold of you? I want to thank you so much for your time today, and thank everyone for attending today's session. This session was recorded. It will be available possibly tomorrow that you can download link to the YouTube video. An email will go out, and please make sure that you take the quick survey after this session or through the email that gets sent to you tomorrow to give us an idea of how well we did and what else we could be doing. And Chris, do you have any last final words?
Not really. Just
Okay.
I guess the main last takeaway is don't get hung up over the cutout temperature. It's a non-issue in my opinion if the objective's reducing carbon. A lot of people that I talk to are really dismissive about the technology at first, but just consider it as an option and investigate it before dismissing it, and you'll see the benefits and go from there.
All right, that's wonderful. Thank you so much. And thank you to everyone for attending. Again, it's being recorded and we'll be sending out a link. So thanks again, Chris.
All right, thanks everyone. Appreciate it, and happy St. Patrick's Day.
Yeah.
All right.